Hello, welcome back. Next, we're going to do one more example under first law of thermodynamics for a closed system. Let's take a look at the diagram first. Here we have a piston cylinder assembly again, slightly more complicated than before. Let's take a look. So first of all, we still have the piston, we still have the cylinder, and inside the cylinder we still have gas, which is within the dash line. Okay, and now let's highlight a few things. So first of all, out of the cylinder, out of the piston, you can see we have pressure coming from the atmosphere. We call it PATM, and this pressure is acting on top of the piston, going downwards, perpendicular and going downwards on the piston. And then at the same time, if you take a look at the other side of the piston, what you notice is we also have pressure coming out of the gas. And this time, the direction of this pressure is going upwards, perpendicular and towards the surface. That's how you determine the direction of pressure. Two rules. First one, it has to be perpendicular to the surface. Next one, it has to be pointing towards the surface. Okay, so we do have to consider those two pressures. And then the third thing I want to point it out is here we have a resistor and battery. So what's happening here is we have electric current going through the resistor. And now as electric goes through the resistor, what's going to happen? The resistor is going to become really, really hot. And then this heat will be transferred to the gas. So gas will gain heat. If the gas gains heat, what's going to happen to the gas? It's going to expand. As the gas expands, it's going to push up the piston. That's how the system works. Okay. All right. So what we know so far is pressure of the atmosphere is given. Here it's 101325 Pascal. Mass of the piston given 45 kilogram. And area, cross-sectional area of the piston is given. It's 0.09 meter square. Okay, where's this A? A is here, indicated by the red surface. This is where the A is. Okay, this surface has an area of 0.09 meter square. Okay, and then we know electric current passes through the resistor, just like we said. It makes the resistor hot, and then heat will be transferred from the resistor to the gas. And then the gas will expand and push up the piston. Okay, initially and finally, gas and piston are at rest, meaning what? Meaning for gas and the piston, the initial velocity and the final velocity are both zero. And next one, no heat transfer other than a resistor. So the only heat transfer, the only Q you need to consider is from the resistor to the gas. You do not have to consider heat transfer such as gas to the environment or anything else. And then another thing, we can neglect the change of the potential energy for gas. And pressure of the gas is constant, P gas is constant. Mass of the gas is given 0.27 kilogram. Delta U, change of specific internal energy of the gas is given 41.87 kilojoules per kilogram. And then last one, delta V, the change of the volume of the gas is 0.05 meter cubic. Because the gas will expand, so if the gas expands, the volume gonna increase. By how much? It's given 0.05 meter cubic. What we're looking for is Q, heat transfer, and pay attention, we want the solution to be in kilojoules. And then we want to do this Q twice. The first time, we choose gas alone as the system. The second time, we choose gas plus the piston as the system. Okay? All right, so that is the question. So next one, let's get started. Solution. We start from the first one, where gas alone is the system. Okay, so now we're looking for heat transfer. What equation have we learned that has Q in it? There's only one. What is that? First law of thermodynamics. So let's go back to our equation for first law of thermodynamics. Where is that? Because here, Q minus W is equal to delta E. So we have to start from here. And before you use this equation, there's one question you always have to ask yourself. What is that? Is my system a closed system? Because this equation only applies if your system is a closed system. So now let's take a look. So now for the first part, my system is gas alone. If you take a look at the dashed line, that is my system. Do you see any inlet or outlet? In other words, do you see mass transfer? Do you see mass going to the gas or mass coming out of the gas? No, I don't. There's no inlet, no outlet for mass transfer. So my system is closed. So yes, I can use this first law. Q minus W is equal to delta E. Okay, so we can start from here. And then just like before, we expand the right-hand side. Delta E, the change of total energy, has three components. The first one is the change of kinetic energy. The second one is the change of potential energy. And then the last one is the change of internal energy. Okay, and next one, what did the question say about the change of potential energy for the gas? Remember, everything, every term in this equation is regarding the system, and my system is the gas. So this term delta PE is the delta PE for gas. And then what did the problem say about the delta PE for gas? Right here. Neglect the delta PE for gas. So delta PE for gas goes to 0. Okay, next one, delta KE for the gas. Delta KE for the gas. What is the initial velocity of the gas? We said gas is at rest initially and finally. So that means the initial velocity of the gas is 0 and the final velocity of the gas is 0. So if velocity is equal to 0, what is kinetic energy? Kinetic energy is also 0, so delta Ke is also 0. There's no change of kinetic energy because at the beginning the kinetic energy is equal to 0 since there's no velocity. And then at the end the kinetic energy is also 0 because there's still no velocity. So 0 minus 0, that is still 0. Okay, so now we rewrite this equation. Since we're looking for Q, so we move Q to the left-hand side and everything else to the other side. It becomes Q equal to W plus delta U. Okay, remember every term in your equation is regarding your system, which is gas for this one. Okay, so now just like we did before, W, we can keep it, but what about delta capital U? I don't know anything about capital U, but I do know delta lowercase u right here. Delta lowercase u of the gas. How do I connect lowercase u with capital U? Let's recall lowercase u is equal to capital U over mass. So delta capital U is equal to delta mass. Don't forget, this is the gas. Okay, mass of the gas. Since gas is my system for now. And then multiply by lowercase u coming from this equation. Rewrite capital U into mass multiplied by lowercase u. And the mass here is the mass of the gas. All right, and then we can continue What about mass of the gas? Does it change? Because delta means change. Mass of the gas doesn't change. It's a constant, so we can pull it out. Mass of the gas and multiply by delta lowercase u of the gas. Okay, do we have mass of the gas? It's given. Mass of the gas is given 0.27 kilogram. And the delta lowercase u of the gas, yes, it is given 41.87 kilojoule per kilogram. Okay, so those two are given. So if we want to find heat transfer Q, the only thing we need to find is work. The only thing we need to find is work. Okay, how do we look for work? I always suggest you start from the most fundamental equation. The most fundamental equation for work is always integral P dV from V1 to V2. P is pressure of your system. V is volume of the system. Okay, so in this case, what kind of pressure is this? Pressure of my system. And my system is gas alone. So the integrand must be pressure of the gas. Pressure of the gas. We need to give it a subscript because we also have PATM, pressure of the atmosphere. To differentiate between those two P's, we give it a subscript. So this is pressure of the gas. Okay, and then what did the question say about pressure of the gas? Pressure of the gas right here. Pressure of the gas is constant. So that means P gas is constant. If P gas is a constant, if you have a constant integrand, what do? You can pull it out. So pressure of the gas, you take it out. And then what is left is V2 minus V1 integration. Okay, all right. So now we have pressure of the gas multiplied by final volume minus initial volume. What is that? Change of volume, delta V. Pressure. So do we have change of volume delta V? It's right here. Right here, delta V is equal to 0.05 meter cubic. So delta V is already given. So if we want to find W, the only thing we need to find is pressure of the gas. If we can find pressure of the gas, we can find W, and then plug in W back into here, and then we can find heat transfer easily. Okay, so next one is how do we find pressure of the gas? Okay, so to find pressure of the gas, we have to perform a balance of forces on the piston. So now we take the piston alone out of our system and take a look at it. How many forces can you think of that are acting on the piston? So first of all, gravity, right? First of all, gravity. How do you write gravity? Mass of the piston multiplied by g. That's gravity going downwards. So the first force is gravity. Second force, let's recall you do have pressure coming from the atmosphere acting on the surface, and the direction is going down. Okay, pressure gives you a force. Pressure multiplied by area is equal to force. Okay, and then at the same time, you also have pressure coming from the gas. Pressure coming from the gas, and it's going upwards. So how many forces do we have in total? Total forces going down must be equal to total force going up. So that's how you balance the three forces. Okay, let's do the left-hand side first. Total force going down. How many forces do we have going down? First of all, gravity. Mass of the piston multiplied by g. So that's the first force going down. What's the second force going down? Pressure coming from the atmosphere, PATM. But here, be careful. We are balancing the forces, so every term here has to be force. For example, this one is gravity, that is force. However, this term is not force. Pressure is not force. How do we convert it to force? Pressure multiplied by area is equal to force. Okay, so this is the second force going down. That's all the forces going down. And they must be balanced by the force going up. What is the force we have going up? It comes from pressure of the gas. And again, this is not force. How do we convert pressure to gas? From pressure to force. So pressure multiplied by area, that is force. Okay, so now remember what we're looking for? We're looking for pressure of the gas. So we do algebra. We move pressure of the gas alone to the left-hand side, and then everything else to the other side. So what we have is PATM plus mass of the piston multiplied by G divided by A. Okay, let's take a look. Do we have everything on the right-hand side? Pressure of the atmosphere is given. It's constant, 101325 Pascal. Mass of the piston is given. G, gravity, 9.8, given. A, cross-sectional area, given. 0.09 meters squared. Okay, so everything in the right-hand side is given. What we do is plug and check. Okay, pressure of the atmosphere, 101325 Pascal. SI unit, and it's given, so that's good. We don't need to convert the units. Pressure, mass of the piston given 45 kilogram. 45 kilogram is given. If you go back to the question, you can find pressure on the sphere given, pressure of mass of the piston given. Okay, 45 kilogram multiplied by G, 9.8, divided by A, cross-section area, which is also given, 0.09 meters squared. Alright, so everything is given in SI unit, and do the calculation, the solution is 106225. Since we used SI unit for every parameter in the right-hand side, your solution will also be in SI unit. The SI unit for pressure is Pascal. Okay, so now we have pressure of the gas. So we go back to here, we plug in delta V, we plug in pressure of the gas, then we find W. And after we find W, what do? We plug in this W back into here, and then we can easily find heat transfer. Okay, so let's plan. Alright, so let's first find W. Like before, we copy down this equation. We said W is equal to pressure of the gas multiplied by delta V, which we derived earlier. Pressure of the gas is given 106225 Pascal SI unit multiplied by delta V, change of the volume, which is also given 0.05 meter cubic SI unit. So solution is 5311.25. And solution must have an SI unit because I used SI unit for every parameter in my right hand side. The SI unit for work is joule. Alright, so I have W now. The last step is to look for heat transfer by using this equation. Alright, so we copy down this equation. Q is equal to W plus mass of the gas multiplied by delta lowercase u of the gas. Okay, W work 5,311.25 and it's SI unit, so that's good. Plus mass of the gas. Mass of the gas is 0.27 kilogram SI unit multiplied by delta U. Delta U is given. It's 41.84. But pay attention to the unit of this number. 41.84 kilojoule per kilogram. Which one is not SI? Kilojoule or kilogram? Kilojoule is not SI. So what we need to do is to convert kilojoule to SI unit, which is joule. Kilojoule to joule times 10 to the third. So now everything in my right hand side is SI unit. Okay, so solution is 16.6 times 10 to the third. Okay, what is the unit to my solution? Like before, because I used SI unit for everything in the right hand side, so my solution must have SI unit. What is the SI unit for heat transfer? Joules. Alright, and then don't forget, what does the question ask for? It asks for Q in kilojoule, so make sure you convert your solution to kilojoule. So 16.6 kilojoule. And again, my solution is positive. If your heat transfer is positive, what does it mean? That means your system gains heat. System gains heat. If your solution for heat transfer is negative, that means your system loses heat. Okay. All right. Does it make sense that my system gains heat? If you take a look, what is my system? My system is the gas. Does the gas gain heat? Yes, it does, because the resistor becomes really hot, so the heat will be transferred to the gas. So the gas does gain heat, and my solution for heat transfer is positive. That makes sense. Okay, you can use that to double check if your solution makes sense or not. So that is our part one. Q, heat transfer is equal to 16.6 kilojoules if we choose gas alone as the system. And next, we do part 2, where we have piston and gas together as the system, different from before. We choose both of them as the system. Like we said, what is a system? System can be whatever you choose to study. So you can choose whatever as your system. Okay. All right, so we're looking for heat transfer again. And again, there's only one equation that we can use that has Q in it, which is first law, which is Q minus W equal to delta E. And before we use this equation, we always have to double check if my solution is if my system is a closed system or not. Let's go back to the diagram. This time we choose piston and the gas together as my system. Do you see any mass going into my system or any mass coming out of my system? Is there any inlet or outlet? No, still, there's no inlet, no outlet. So my new system is still a closed system. That means I can still use this first law, developed for a closed system. And then we do the same thing again. This time delta E will be expanded into three terms again: change of kinetic energy, change of potential energy, and change of internal energy. Okay, and now remember this. Every term in this equation is regarding your system, and my system now has changed. My system now is piston plus the gas. So for example, this term, delta capital U, the change of internal energy is no longer the change of the internal energy of gas alone, but the change of internal energy for the piston and the gas. Okay, same thing happens for every term in this equation. Okay, remember we're looking for heat transfer, so what we do is to move Q to the left hand side and everything else to the other side. So it becomes W plus delta KE plus delta PE plus delta U. Okay, so let's find every one of them in the right hand side. If we can find every single term in the right hand side, we will be done. Okay, so let's start from the easiest one. Let's start from delta KE. Okay, let's start from delta KE. Delta KE. Okay, delta KE is the change of kinetic energy. So that means final kinetic energy minus initial kinetic energy. Okay, kinetic energy is 1 over 2 times mass times velocity squared. V2 means final velocity, V1 means initial velocity. Delta change, whenever you calculate change, is always final minus initial. All right, and mass, what is the mass here? Mass of your system. Okay, mass of your system. In this case, my system is piston plus the gas. So mass of the system must be the mass of the piston and the mass of the gas. Okay? All right, let's recall what is V1 and what is V2. If you go back to the question, what does the question say about it? Here, gas and piston are at rest initially and finally. So for gas and the piston, which is my system now, the initial velocity v1 and the final velocity are both zero because at rest, right? So now we can go back. We can see v1 is equal to 0, so the second term goes to 0. And v2 is equal to 0, so the first term goes to 0. Okay, because v1 is equal to 0 and v2 is equal to 0 at rest. So delta Ke is equal to 0. So delta Ke found. That's easy, huh? Okay, next one, let's do delta Pe. Next one, let's find delta Pe. Okay, delta Pe. Delta P of my system. And my system consists of two components. They are delta P of the piston and delta PE of the gas. Okay, so remember my system now has two components, piston and the gas. Okay, what did the question say about delta PE for the gas? If you don't remember, let's go back to the question. The problem said you can neglect the delta PE for gas. That means delta PE of the gas can be neglected. Second term in the right hand side goes to 0. So I only need to find delta PE of the piston. How do I look for delta P of the piston? The change of potential energy is what? Mass times G times the change of the height. So mg delta Z. And then what is my mass here? Mass must be the mass of the piston. Okay, let me rewrite it. Mass of the piston times G times delta Z. Okay, do I have mass of the piston? Yes, 45 kilograms is given. Do I have G? Yes, G is 9.8, it's constant. All right, so the only thing we don't have is change of height. So we know the gas will expand and then it's gonna push up the piston. So the piston does change in terms of height. So there is a delta Z and it's not equal to 0. And what is it? What is it? So if you look at the diagram again, okay, so let's sketch the diagram here. This is the cylinder and this is where my piston is initially. Okay, and then because we know the gas is gonna gain heat, it's gonna expand, so it will push up the piston. So finally, the piston will be pushed up to a new position. This is the initial position, this is the final position. And now we're looking for delta Z, the change of the height of the piston. If we can find delta Z, we can just plug it in here and find delta PE. Okay, how do I find delta Z? All right, let's recall. Do you remember? So what is this here? What is the volume here? What is this? This is the change of the volume, right? This space here is the change of the volume of the gas. This is delta V. And what is the shape of this volume, this delta V? It's a cylinder. It's a cylinder because the piston is a circle if you look from above, right? It's a cylinder. How do you calculate the volume of the cylinder? The volume of the cylinder is delta V. How do you calculate the volume of a cylinder? The cross-sectional area, which is A, and then multiply by the height, the length of the cylinder. What is the length of the cylinder in my diagram? It's delta Z. Okay, so this is the equation. So can we rewrite delta Z from this equation? Yes. Mass of the piston times G and times delta Z. What is delta Z from this equation? It's delta V over A. Mass of the piston given G 9.8, delta V given, cross-sectional area given. So now I have everything in the right-hand side. Okay, so we're plugging everything. 45 kilogram multiplied by 9.8 SI unit. Delta V is given 0.05 meter cubic SI unit. Cross-sectional area 0.09 meter squared, also SI unit. So everything is SI unit. My solution is 245. Must be SI unit, so joule. So now I have found delta PE. The second term in my right-hand side, the third term in my right-hand side has been found. Okay, and next let's look for delta U. Delta U. What is the change of internal energy for my system? Okay, what is delta U? And then we do the same thing again. The system has two components. The first one is the piston. The second one is the gas. So it has two components. Delta U from the piston and delta U from the gas. Okay, so let's do the same thing. Let's recall lowercase u is equal to capital U over m. So let's rewrite the first delta U. The first one can be rewritten to mass of the piston multiplied by U of the piston. The second one can be rewritten to mass of the gas multiplied by lowercase u of the gas. Okay, and again, does mass of the piston change? No, it doesn't, so you can take it out. Does the mass of the gas change? No, it doesn't, so you can take it out. Okay, so it becomes mass of the piston multiplied by delta U of the piston plus mass of the gas multiplied by delta U of the gas. Okay, mass of the gas is given. Delta U of the gas is also given. Mass of the piston is given. So the only thing we want to find out is delta U of the piston. Delta U of the piston. What does it mean? It means the change of the internal energy of the piston. Okay, so this is really interesting. We said before, what is internal energy? Internal energy is represented by the temperature of this object. So, for example, if you have a pot of water and then the temperature of this water doesn't change at all, do you think the internal energy will change? No, the internal energy will not change. Okay, so now let's take a look. Does the temperature of the piston change? Does the temperature of the piston change? Let's take a look at the piston. Right, does the temperature change? For the temperature of the piston to change, there has to be heat transfer, right? So do we have heat transfer either going into the piston or leaving the piston? Because if I do have heat going into the piston, the temperature of the piston will go up. All right, so what did the question say? No heat transfer other than the resistor. So the only heat transfer you have to consider here is from the resistor to the gas. And there's no any other format of heat transfer. If that's the case, that means there's no heat transfer either going into the piston or coming out of the piston. If there's no heat transfer, does the temperature of the piston change? No, the temperature of the piston doesn't change. And if the temperature of this piston doesn't change, does the internal energy change? No. Okay, so now we can go back to our equation and say the internal energy of the piston does not change. So the change delta U for the piston must be equal to 0. Okay, so that is the reason. Alright, so the first term goes to 0 and then the only thing left is mass of the gas multiplied by delta U of the gas. We have both of them. Mass of the gas is 0.27 kilogram. Delta U of the gas is 41.87. And be careful about the unit here. Remember, this is given in kilojoules per kilogram, so we need to convert the non-SI one, which is kilojoule, to SI, which is joule, by times 10 to the third. Okay, so our solution is 11.34 times 10 to the third SI unit joule. Okay, so that is my delta U. And now let's continue. Let's go back to our this equation, heat transfer. Now I have found the last term in the right-hand side, delta U. Okay, so the only thing left for me to solve this question is to look for the first term in the right-hand side, which is work. Okay, so now we look for the last thing in the right-hand side, which is work. How do we look for work? Like we said, I always suggest you start from the most fundamental equation. What is the most fundamental equation for work? Integral P dV from V1 to V2. Okay, and now this time, what is the pressure? Is it P ATM or is it P gas? This is always P of your system. The integrand must be pressure of your system. V1 to V2, so must be pressure of the system. And dV. Okay, so what is pressure of the system? I don't know. Last time it was much easier. Why? Because last time if you take a look, integral PdV, pressure of the system. Last time the system is the gas alone. So the integrand is just pressure of the gas. And we know it's constant, which is a given, so you can take it out. But this time, my system is no longer gas alone, it is gas plus piston. So what is the pressure of my system this time? Okay, it's not that difficult to find. Let's continue. Okay, let's sketch the diagram again. This is the cylinder and this is the piston. And what is my system? This time my system is piston plus the cylinder. So you draw a new dashed line, including both the gas and the piston. And everything under this top dashed line is your system. So now, just like before, on top this surface, you still have pressure of the atmosphere acting on it going down. And then this time you also have pressure of the system acting on it, but upwards. Right? Remember the direction of pressure is always pointing towards the surface. Pressure of the system. Okay, so now what we're going to do is to balance all the forces on the surface, this dash line. This dash line. We're going to balance all the forces acting on the surface. How many forces can you find acting on the surface? Do we still have gravity? No, because we're looking at a surface. A surface doesn't have volume. If it doesn't have volume, it doesn't have mass. If there's no mass, there's no gravity. So the only two forces we can find is first one coming from the atmosphere. Pressure of the atmosphere multiplied by area. That's one force going down. And it must be balanced by the force going up, which is pressure of the system multiplied by area. And then the two areas cancel each other. So what we can say is pressure of my system is equal to pressure atmosphere. So now I can plug in my solution back into here. So this becomes V1 to V2 and pressure atmosphere, and then times dV. Okay, what do we know about pressure of atmosphere? It's a constant, so we can take the integrand out of it. And what is left is V2 minus V1, and then becomes pressure of the atmosphere multiplied by delta V. V2 minus V1, final volume minus initial volume, that's change of volume, delta V. Okay, so now we do plug and chug. Pressure of atmosphere is 101325 Pascal. 101325 Pascal SI unit multiplied by change of volume 0.05 cubic meter. So solution is 5066.25 and the unit must be SI unit, joules. Okay, all right, so now let's go back to our equation and what do you notice? We just found work. And now we have found everything in the right-hand side. Okay, so now what we do is we plug them in. Okay, Q, copy down this equation. Q is equal to W plus delta KE plus delta PE plus delta U. Okay, let's do the first one. W, we just found W right here, 5066.25. And it's in SI unit. Okay, next one, delta KE. Do you remember what delta KE is? Delta KE here is 0, so plug in 0. Plug in delta PE. What is delta PE? Delta P is right here, 245 joules. 245. And then the last one, delta U. What is delta U? Right here, 11.34 times 10 to the third joules. Okay, so we have everything in the right-hand side. Then the solution is 16.6 times 10 to the third SI unit joules because I used SI unit for every term in the right-hand side. And then one more step, 16.6 kilojoules. Convert joules to kilojoules. Okay, so now if you take a look, what was our solution from part 1? Our solution from part 1 was 16.6 kilojoules. And what is our solution from part 2? Exactly the same, 16.6 kilojoules. Again, Q positive, system gains heat. So it really doesn't matter what kind of system you choose, the solution is the same. So what does this example tell you? It tells you even though you can choose anything as your system to study, but choosing an appropriate system can make your calculation much easier. So for example, this one, part 1 and part 2, which one you think is easier to calculate? Obviously part 1.